I'm back.
3 oil companies have submitted bids for satisfying fuel requirements of 4 Air Force bases. We have the problem information in this table. Companies 1, 2, and 3. Also bases 1, 2, 3, and 4. This is the bid information. So dollar per 1,000 gallons of fuel. So it means that company 1 will supply 1,000 gallons of fuel to base 1 for $500 and so on. This is the fuel requirement of each base, and this is the production capacity of each company. So company, for example, company 1 can supply up to 50,000 gallons of fuel. Now we want to formulate, so the Air Force wants to select the best bids. Okay, so it's a cost minimization formulate an integer program to minimize the cost of meeting the fuel requirements given the following constraints. Okay, without the constraint, let's forget those constraints. If it was the problem, this was the problem, this was all we knew without any additional constraint, its formulation was very easy, right? But what makes it complicated is the constraints that are introduced in here. Okay, the problem is not that easy because in addition to satisfying the fuel requirement that we have in here and also considering the production capacity of each company as well as the cost that we have in here, we also have to consider some additional limitations. We have to model some other conditions too. One, company 1 has specified that for base 1 a minimum acceptable demand of 15,000 gallons, which means that, okay, we will discuss its meaning later. Let me read them all. Company 2 has specified that at least 2 of the following conditions must be satisfied: supply of at most 10,000 gallons to base 1, or at least 5,000 gallons to base 2, or exactly 7,000 gallons to base 3. So at least 2 of these conditions must be satisfied. Company 3 has specified that the total amount to all bases must be a multiple of 10,000 gallons. Also, company 3 has specified that if it supplies more than 15,000 gallons to base 1, it must also supply at least 20,000 gallons to base 2. Okay, now let's consider these constraints one by one. Before coming to these complicating constraints, let's formulate the problem regardless of them. Then we will add constraint corresponding to these conditions later. Okay? It is natural to define our variables like xij, where xij represent the number of 1,000 gallons fuel supplied by company I to base J. So when we solve our problem, it will give us the exact amount that the Air Force wants to buy from company 1 for base 1, from company 1 for base 2, from company 1 for base 3, and so on. Okay, like before, in order to have a compact formulation, let me introduce some parameters. So like before, I denote the production capacity of company I by BI, the demand of base J, by DJ, and the cost of the supply cost from company I to base J by Cij. Then it is easy to see that this is the basic formulation without considering the complicating constraints, right? So the summation of all terms Cij times Xij. We also want that the summation of all supplies to base J be greater than or equal its demand, and also the summation of supply by each company cannot exceed its capacity. Of course, every variable is a non-negative variable. So a very natural, we have seen a very natural formulation. We have seen a formulation like this multiple times. No problem so far. Now let's consider the additional constraints one by one. So remember, the point is every company has specified some special conditions. Okay? So if we just solve this problem and we get the solution, that solution might violate some of those conditions. Okay, so that bid will not actually become a contract. In order for that to happen, we have to consider the company's conditions too. And we are going to do that one by one. The first condition is that company 1 has specified that the minimum acceptable demand or minimum acceptable order for base 1 is 15,000 gallons. Okay, what does it mean? It means that two cases are feasible. Okay, two cases might happen. Let me write them down. The first case, the first acceptable case, is that company A sends more than 15,000 or more to base 1. So company A supplies greater than or equal 15,000 gallons to base 1. Or what is the other possibility? The other possibility is that it provides nothing to base 1 because it says that this is the minimum acceptable. Okay, less than this, I cannot do that. Okay, so the other case is company A supplies 0 gallons to base 1. Okay, mathematically speaking, the supply of company A, sorry, I should say company 1 to base 1, X11 represents the amount of fuel supplied by company 1 to base 1. So this is greater than 15 because our unit is, remember, our unit is, everything is in terms of 1,000 gallons. So X11 is greater than 15, or X11 is 0. Right? Actually, this is a bit difficult for us to apply that technique to a constraint like this, but note that this is actually equivalent to say X11 is less than or equal 0, right? Because we know that the value of X11 is not negative, so if also it is required to be non-positive, it means that the only possible value that it can get is 0. Okay, so instead of this, I'm saying this or this. See, this is an either or condition. So, and I want to switch between them, like what I explained about the sets A and B in the previous example. Okay, now I have two constraints and I want to introduce a binary variable to switch between them. So for this one, so I introduce a variable y, a binary variable. Then instead of writing x11 greater than or equal 15, I write x11 plus a very big number.
It's very, very big.
Times y is greater than or equal 15. Okay, in this case, let me explain it again. If y is 0, it is the original constraint. I mean this one. If y is 1, it becomes redundant. For the other constraint, I want if y is 0, I want it to become redundant, so it is the same switch. For y equal 1, I want it to be original. Okay, so it can be x11. Here I'm using this one, less than or equal 0 plus m times 1 minus 1. Okay, so I can use these two constraints with an additional variable y. I can add those to my formulation to model this extra condition that company 1 requested. Okay, but as I said, there is still one thing left to remember from our last discussion, the last lecture, and that was the value of big M. Okay, we prefer not to leave it like this. So the question is, how big should M be?
Wait! I haven't told you what it is yet.
My claim is, in this case, 15 is good enough. Why? Because remember, y is 0 or 1. If it is 0, the value of m doesn't matter. If it is 1, we want this constraint to be redundant. Okay? And if it is 1, then this term becomes 15. And we know that x11 is actually non-negative. So x11 cannot be less than 0. So in any case, 15 plus 0 or some positive number is required to be greater than 15, which is trivially satisfied. So 15 as the coefficient of y in here is enough. So x11 plus 15y greater than or equal 15. How about this one? x11, I move every variable to the left hand side, so it becomes m times y. My claim is 50 is enough, less than or equal 50. So I chose 50 for this one. Remember, if y is 0, I will have x11 less than 50. Okay? And 50 is the total, is the supply capacity of company 1. It is obvious that x11 cannot be, let me go here, so you cannot see it here, but this is 50 is the supply capacity of company 1. So x11 less than 50 is a redundant constraint. Okay, the capacity constraint that we have included in our formulation makes sure that 50 is enough. Okay, and in case that its value is 1, then we will have x11 plus 50 less than or equal 50, which is equivalent to x11 less than or equal 0, our original constraint. Okay? So in order to, once again, in order to model this condition, we just need to add these two constraints to our original formulation. This is what we discussed. This condition is an either or condition, either this or this, mathematically this constraint or this constraint. And in order to switch between these two constraints, we introduced a new variable and incorporate that variable associated with a very big number, and we end up with two constraints like this, and add these two constraints to the formulation that we already have. Okay, so case 1, the requirements of company 1 is already taken care of. Now let's move to the requirement of the second company. The second company says that I have 3 conditions and you have to satisfy at least 2 of them. Okay, the first condition is that I can give at most 10,000 gallons to base 1. The second one is that I can give at least, I must give at least 5,000 gallons to base 2. So the order for base 2 must be greater than or equal 5,000 gallons. And the third condition is that I can give exactly 7,000 gallons to base 3. You should satisfy at least 2 of them, okay, in order for us to make a contract. So we want to incorporate them in our formulation. Now it is easy for you to see that mathematically we are talking about the supply from company 2 to base 1 cannot exceed 10,000 gallons. From company 2 to base 2 must be greater than or equal 5, and from company 2 to base 3 be exactly 7. And we have to, it is not a simple switch. Okay, now we have 3 conditions and we want to satisfy at least 2 of them. The first thing that we should do, I mentioned this before, this type of constraint is hard to work with, so I decompose it. Remember that x23 equal to 7 is equivalent to 2 constraints, greater than or equal 7 or less than or equal 7. So instead of this, I will use these 2 constraints. Okay, they are tied together. They represent a single case. So this is case 1, this is condition 1, this is condition 2, this is condition 3. Now I cannot model this using a single binary variable. Instead, I will need 3 binary variables. And you will see why. And you will see that the case that I presented before is actually a special case of this. So I will introduce, let's call it y1, y prime 1, y prime 2, and y prime 3. So y prime 1, y prime 2, y prime 3, all 3 of them are binary variables. Okay, now I want to use y prime 1 on this one, y prime 2 on this one, and y prime 3 on this one, such that if the corresponding binary variable takes on a value 1, that constraint becomes redundant. Okay, so what I want is if y prime 1 is 1, then condition 1 is not satisfied. Okay, not satisfied means from the viewpoint of company 2 it is not satisfied. Okay, it means that I'm just ignoring that condition. Okay, or I'm making the corresponding constraint redundant. Okay, we know how to do that, right? So I have x21 less than or equal 10. I want to use x prime 1 such that if x prime 1 is 1, then this constraint becomes redundant. Obviously, x21 less than or equal 10.
Pause for effect.
A very big number times y prime 1. Then if y prime 1 is 1, I will have x21 less than or equal a very big number. So it is trivially satisfied. In other words, this value of y prime 1 makes this constraint redundant. And if its value is 0, I will get the original constraint of condition 1. Great? Okay. Now I want to do the same with y prime 2 and y prime 3. So if y prime 2 is 1, I want this constraint to be redundant. So the constraint is x22 greater than or equal 5. In order to make it redundant with y prime 2 equal to 1, I just need to add y prime 2 with a very big coefficient to the left hand side, right? So x22 plus m y prime 2 greater than or equal 5. Again, observe that if y prime 2 is 1, I will have a very big number greater than or equal 5, which makes the constraint redundant, trivially satisfied. And if its value is 0, I get the original x22 greater than or equal 5 constraint. Now let's do the same with the last set of constraint. This is the constraint of condition 3. So I have x23. I'm going to use x prime 3 in order to make this redundant. M y prime 3 greater than or equal 7. Remember, I have two constraints. Both have the same binary variable, less than or equal 7 plus m y prime 3. So if y prime 3 is 1, for the first one I will get a very big number greater than or equal 7, and for the other one I will get x23 less than or equal to a very big number, again trivially satisfied. So with the value of y prime 3 equal to 1, I will get rid of this constraint, and setting y prime 3 equal to 0 will lead to the original condition 3 constraint. Right? Are we done? No. Still, we haven't specified the relation between these three. Okay? So far, we know that every binary variable, by taking a value 1, can make the corresponding constraint redundant. But the condition is that out of these three, only one of them can actually be 1, right? Because the condition says that out of these three conditions, 2 of them must be satisfied, which means that you can ignore just one of them. You can make only one constraint among them redundant, right? So in addition to these three, we have to add y prime 1 plus y prime 2 plus y prime 3 less than or equal 1. In other words, you should either satisfy all these conditions or at most one of them can be ignored. Okay, so let me also put this in a box. These A, B, C, and D, these four are the constraint that we need to add to the original formulation in order to model the conditions of company 2. Okay, all of them, and it will perfectly model what the second company wants. Let me erase them because I have the solution in the other page. Here it is, exactly what I explained. So we have three constraints. This one, and the combination of these two, and we use three binary variables to come up with this set of constraints that model the requirement of the second company. Now let's go to the requirement of the third company. Okay, the company 3 has specified that the total amount to all bases must be a multiple of 10,000 gallons. This is actually an easy one, right? What is the total amount that the company 3 supplies? Remember, Xij was the amount of fuel, 1,000 gallons is our unit, the fuel supplied by company I to base J. Okay, so the total amount that company 3 supplies is what it supplies to first base plus what it supplies to the second base, what it supplies to the third base, right? And it must be an exact multiple of 10,000 gallons. Okay, we just need to introduce an integer variable. Let's say W. So say this must be, remember that our unit is 1,000 gallons, so if this W is integer, this sum must be an exact multiple of 10,000 gallons, and that's it. And of course that it is integer and non-negative. Let's have a look at the last condition. Oh, this is the solution. Okay, so this is exactly what we had. So you expand it, you get x31 plus x32 plus x33 equal to 10 times an integer value W. Okay, let's have a look at the last condition. Company 3 has also specified that if it supplies more than 15,000 gallons to base 1, then it must also supply at least 20,000 gallons to base 2. Okay, this means, in order to see this either or pattern in here, this means that the third company, there are two cases. Case 1, the third company, this company supplies less than. So company 3 supplies, say, no more than 15,000 gallons to base 1. This is the first case. Or it will supply more than this amount, right? If it supplies more than this amount, then it must also supply at least 20,000 gallons to base 2. Okay, so or it supplies at least 1,000 gallons to base 2. The first case, mathematically, it means that the supply of the third company to base 1 is less than or equal 15, and the second is the supply of X32, the supply of the third company to the second base is greater than or equal 20. Either this happens or this happens. Okay, this is equivalent to this condition, and in order to model this or relationship like before, we add y, which can take on 0 or 1, and use these values to switch between these two conditions. So the first one becomes 31 less than or equal 15 plus a big number. Let me make it, I've used y before, so y double prime. So in case that y double prime is 1, this constraint becomes redundant, and if it is 0, then this constraint is in effect. I want to use the same switch, so the other constraint should be like this. I have to use 1 minus y double prime. So if the value of y prime is 0, then this constraint becomes redundant. And again, let's try to find appropriate values for m. So let's see, X31 less than or equal. Remember that the third company cannot supply more than 60,000 gallons of fuel in total. Okay, let me check this value again. Yes, the third company cannot supply more than 60,000 gallons. So a condition like this less than or equal 60 is enough for me. Okay, so in case that y double prime is 1, I want to have something like this. So 15 plus 45 y double prime, it is enough. Okay, so if y double prime is 0, it becomes my original constraint. If y double prime is 1, it becomes X31 less than or equal 60, which is enough for my case, because I know that the third company cannot supply more than $60,000 or 60,000 gallons in total. How about the other constraint? 32, and here let's see what is an appropriate value for this. 20 is enough, because if I put 20 in here, we had something similar to this before. Then in case that y prime is 1, then I will get the original constraint. If y double prime is 0, if y double prime is 0, then I will get X32 plus 20 greater than or equal 20, or simply X32 greater than or equal 0, which is a non-negativity constraint that makes this, I already have a non-negativity constraint, right, which makes this trivial. So 20 is enough, and I actually can't expand this. So if I expand it, it becomes, so 20 y prime minus 20 y double prime greater than or equal to 0. Okay, these are the constraints that I will need to model the second, the last condition. I believe for the second condition I didn't specify the values, the actual values of big M. I just forgot it, but I have the actual solution in the next slide. In the slide after this, this is exactly what we came up with. Right, we just need to add these constraints to model this condition. Remember that company 3 had two requests. The first one was that its total supply must be a multiple of 10,000 gallons, and this is the second condition. For the first condition, we have to add one constraint, as I showed, and here we have to add 2 constraints, so 3 constraints in total for to consider to model the conditions of the third company. And here is the actual model. So we have added all the constraints that we derived. This part is the base formulation that we started with. The objective is just cost. We also have the demand constraint. We also have the capacity constraint. And these are exactly the constraints that we came up in order to model the requirements of the company. So this was for the first company. These are for the second company, and I believe one of them is missing.
I saw that with my own eyes.
Because we are supposed, yeah, the one that, I'm sorry, it should be, it is not in this slide, I remember. So for the first condition, this is the first condition. We had 2 constraints, that is correct. For the other one, we had 1, 2, 3, 4, 5. In particular, the first one corresponded to this, so it started with a variable x21, but it's a typo in that. So this is the correct set of constraints, but this constraint is missing in the final formulation. Remember, it's this constraint, it's a typo. This constraint must be there. So the one that starts with 2,1 should be somewhere here. Then we have 1 constraint for x22, and these are the constraints that we built based on this original constraint, remember? And this says that out of the requirements of the second company, at least 2 of them must be satisfied, or equivalently you can ignore at most 1 of them. And the requirements of the third company are here. This is the multiple of 10,000 gallons condition that the company requested, and these are the latest constraint that we came up with. Of course, we introduced 1, 2, 3, 4, 5, 6 new variables other than the original variables. These are the physical variables. Y and y prime 1, y prime 2, y prime 3, and y double prime are the binary variables that we introduced. We also introduced an integer variable denoted by w, which is non-negative and integer. This is the final model for this problem.